In Chapter 6 of Year 2 Pure, we're going to look at some more trigonometry following on from the Year 1 content. And we've got three new functions that we're going to look at. And actually, it turns out that they're not really that new at all. They're just based off the three that we already know. These three new functions are sec x, cosec x, and cot x. Or obviously, it doesn't have to be x, it could be theta or whatever you're calling your angle. Now, the ways that these are defined, sec x is actually just 1 over cos x. Cosec x is 1 over sine x. And cot x is 1 over tan x. Okay, so these are not really new functions, it's just a different way of writing 1 over the other functions that we knew already. Now, in terms of remembering which one's which, you might think is a little bit counterintuitive having cosec actually be sine rather than cosine. But the way to remember it is to look at the third letter. Okay. So sec, the third letter is cos. Cosec, the third letter is s, so it's sine. And cot, the third letter is t. Okay, so that will help you remember it. Now, the next thing I want to think about is what the graphs of these functions look like, because we already know what sine, cos, and tan look like. So let's try and work out what 1 over each of those functions looks like. So we're going to look at sec x first. And actually, I'm just going to plot these in degrees first, just because people tend to be more comfortable with degrees, but you can obviously plot them in radians yourself afterwards. So sec x is 1 over cos x. So to plot this, I'm just going to look at the graph of cos x first of all. So the graph of cos x usually looks like this, with 0, 90, 180, 270, and then this point here at the end is 360. Okay, so this is cos x. Now if I'm going to do 1 over that, I'm going to use the same scale between 0 and 360. We can just consider the value of the graph at some key points and plot them. So at 0 degrees, cos is equal to 1. 1 over 1 is still 1, so it's still going to go through that point there. At 90 at 0, 1 over 0 is undefined. You can't divide by 0, it's undefined. So we actually don't get a value there, and so it generates an asymptote there. At 180, it's minus 1. 1 over minus 1 is still minus 1, so it goes through minus 1 down there. At 270, it's 0 again, so again 1 over 0 is undefined, so we get an asymptote. And at 360, it's 1 again. 1 over 1 is still 1. So we've got a couple of points, and we've got a couple of asymptotes. Now, in terms of the general shape, between 0 and 90, cos gets smaller and smaller. So if we're doing 1 over something that gets smaller and smaller, it's actually going to get bigger. So it starts here and it gets bigger towards this asymptote like this. Here, between 90 and 180, it starts small and gets more negative. Okay, so it's going to come in like this. Okay, and then beyond 180, again, it becomes smaller, it becomes closer to 0. So we're dividing by, so maybe here we're dividing by negative 2/3. Here we're dividing by minus 0.01. So it's going to be much bigger, so it's going to go away like this. Okay, and we've obviously still got this asymptote down here. In the last section, it still goes through the 1. Between 270 and 360, it's getting larger, so we are dividing by something bigger and bigger, so it gets smaller down here. Okay, so this is the general shape of the graph. Obviously, it continues. It doesn't just get cut off at 360, it keeps going. You can actually plot these on Desmos if you like, so you could plot sec x and it understands that as a function, and there it is. So you get this repeating sort of U shape. Okay, let's have a look at the next graph, cosec x. So this is 1 over sine x. We're going to do it by exactly the same method. So I'm just going to sketch sine x. You might want to have a go at sketching it yourself and then watching the video and seeing if your prediction was right. But here's sine x normally, so 0, 180, 360, 270, 90. Now if we're going to do 1 over that, I'm going to just do the same scale again. Okay, let's pick out some key points again. So at 0, the value of sine x is 0. And like we said before, 1 over 0 is undefined, so that's going to generate an asymptote. So I'm just going to do a dashed line down here. At 90, sine x has the value of 1. 1 over 1 is still 1, so it's going to go through that point. At 180, it's 0, so you get another asymptote. At 270, it's minus 1. And at 360, it's 0, so we get another asymptote there. And in terms of the shape, it's going to match the graph of sec x as well. But let's just think about it again. We're increasing in value here, so we're doing 1 over something bigger and bigger and bigger. And so this is going to get smaller and smaller in value as we go from 0 towards 90, down to the smallest value of 1. Then between 90 and 180, we're going from 1 down to 0. So it's going 1, then 0.9, 0.8, 0.7, and so on. So this then gets bigger and bigger and bigger. And we get the opposite shape down here, but just for negative values, so this sort of shape. And obviously just make sure it doesn't cut through the asymptote. Okay, it tends towards those values, but doesn't quite intersect with them. And again, you get this pattern repeating. So if we were to sketch it on here, cosec x so if we sketch it, then it will look like that. It wouldn't let me type in cosec x for some reason, but I just typed it in as 1 over sine x, and you can do it that way too. Okay, the last one then is cot x, which is 1 over tan x. So again, we're going to start by just drawing the graph of tan x. Okay, so this is just between 0 and 360. Okay. Now we're going to draw 1 over tan x underneath it. So in terms of some key points, we've got a 0 here at 0. Actually, let's just fill in the axis properly. Okay, so 1 over 0 is undefined, so we're going to get an asymptote here. Now at 90, we've actually already got an asymptote. Now it's a bit weird to think of 1 over an asymptote, because that's not really mathematically what's going on, but it does do what you would expect. It does the reverse of what happened before, so actually this generates a 0. Okay, so it's going to go through this point here. At 180, it's 0, so we're going to get an asymptote there. At 270, we had an asymptote, so that's going to generate a 0. And then at 360, it's 0, so 1 over 0 is undefined, so we get another asymptote. Okay, now we need to think about the actual shape of the graph. So we've got some asymptotes and we've got some points that it goes through. In this section here, where it's increasing in value, the number is getting bigger and bigger and bigger. Remember as well that tan can be bigger than 1, so it could be like 3, 4, 5, and so on. So as this gets bigger, 1 over that value must be getting smaller. So it's going to start off really big because it's 1 over, say, 0.1 or 0.001, and then it's going to decrease in value as this goes up. So we're going to start high and come down lower. And then beyond 90, this bit is negative and going towards 0. So it's going to look like this. And then the pattern just repeats in the next section as well for the same reasons, because we've got this graph is just repeating every 180, so this graph is repeating too. So it looks like that. Okay, and that's the graph of cot x. And again, you can plot these on Desmos if you want to play around with them as well. Okay, let's do cot x. So 3 new functions there, but actually they're not really new functions. Okay, they're just 1 over the other ones that we use. Okay, in this next example, I want to keep thinking about the graphs of these functions. And I also want to do a bit of a reminder about using some graph transformations. So sketch a graph of y equals 4 cosec x between minus pi and pi. So to do this, I think I'm going to just start off by thinking about the graph of sine x again, okay? Because remember, cosec x, the third letter, so this is 1 over sine x, okay? Or you could think of it as 4 times 1 over sine x, okay? Now let's just look at the graph of sine x, and we've got to plot it between minus pi and pi. I'm going to plot it just between minus 2 pi and plus 2 pi, because that just tends to be how I think of these graphs in sort of sets of 2 pi. So the graph of sine x looks like this. So this is going to be 2 complete waves. So this is between minus 2 pi and 0, and then between 0 and 2 pi, it will look like that. Okay. So the graph of 4 cosec x, the 4, all that's going to do to my cosec graph is vertically stretch it by 4. Okay, hope you remember back when we did this for the year 1 content, that would be 4 lots of f of x, so a vertical stretch of 4. Okay, let's draw the cosec graph. So here's 0, now I've got minus 2 pi, minus pi, pi and 2 pi. Asymptotes are going to be here and here, get my zeros. And then it still goes through 1 and minus 1, minus 1 and 1. And it's 1 over that, so the shape looks like this sort of thing. Okay. Now the only difference we said was that it's vertically stretched by 4. So normally on the cosec graph, this height here would be 1. But if we're vertically stretching it by 4, instead of 1, it's just going to be 4 instead. Okay. And likewise, this point is going to be at minus 4. That's the only real difference. Okay. Now, the question said to just plot it between minus pi and pi, so really we just want this section here, but I don't think they're going to penalise you for drawing too much of the graph. In part C, state the number of solutions to the equation 4 cosec x minus x equals 0. Well, actually, we forgot to do part B, but we could do them together. On the same axis, draw the line y equals x. So line y equals x is obviously a line with gradient 1, but it could look like, depends how you draw it, so it could look like this, or it could look like, don't know, this. Depends on our scale. Now, let's think carefully about the scale of this axis. If this is pi, maybe it helps to think of these in numbers. This is 3.14. This point here is pi over 2, that's 1.57-ish. So if the line is y equals x, then when x is 1.57, the y-axis is also going to be 1.57. So it's probably going to be about there. Now when it's pi, it's going to be 3.14, so maybe that's about there. Okay, we're going to get obviously the same gradient throughout down here. So if we draw this line on, okay, it's going to look something like this. Okay, but the important thing here is that you've got an approximate sort of scale for the gradient on here, but that they don't intersect between pi and minus pi. Obviously they will intersect later on, so beyond pi they will intersect a curve that's up here somewhere. But between just minus pi and pi they don't intersect. Now the intersections of the black curve and the red curve, that would be solving 4 cosec x equals x. Okay, because this is y equals this and y equals this. So the intersections of these two graphs would be solved by this equation here, which is also equivalent to this equation here. Okay, So this has got no solutions because there's no intersections. So therefore this has also got no solutions. Okay. So between minus pi and pi, there's actually no solutions to that equation. Beyond pi, there probably is, because this graph obviously keeps repeating itself, so they will eventually intersect, but not in that limit. For this next example then, so we've got to plot this one in degrees between 0 and 360. 1 plus sec 2 theta. So we're going to think about this in stages, just like we did when we did transforming graphs before. So first of all, let's just draw cosine theta, probably be the place to start, because if we're doing sec, third letter is C, so this is based on cos theta. So cos theta obviously looks like this, 0, 180, 90 there, 270, 360. So the graph of sec theta is going to look like this. So we are going to have a value of 1 at 0, an asymptote at 90, minus 1 at 180, an asymptote at 270, and then 1 again at 360. And the shape looks like this sort of thing. Okay, so that's the graph we're basing it on. Now, in terms of how this has been transformed, the first thing that's happened, so if we say that f of x, or f of theta, I suppose we should say, is sec theta, the first transformation is f of 2 theta. This is a squash horizontally of scale factor 2. Okay. The next thing that happens is then f of 2 theta plus 1, which moves the whole thing up by 1. Okay. Now let's deal with the horizontal squash of 2 first of all. Maybe think about what happens to cos theta first. If I transform that to cos 2 theta, then it would look like this instead. Okay. So instead of one wave, I now get 2 waves in the same space, is the way to think about it. Okay. So the same thing's going to happen here. I'm basically going to get this pattern here, but repeated twice in the same space. So I'm just going to draw it again. So what I'm drawing here is sec 2 theta. So I'm going to keep the scale the same. Okay. So this asymptote is going to move twice as close to the origin. So instead of being an asymptote at 90, it's going to be an asymptote at 45. Okay. And we're going to get this shape here between 0 and 45, rather than between 0 and 90. Now the next asymptote, it was at 270, but it's going to be at half of that, so it's going to be at 135. So it's going to be down here, 135. And we're going to get that N shape down here. Now the next asymptote, after this one, it would have been at 360 plus 90. So 360 plus 90. The next asymptote would be at 450. It's now going to be twice as close as that. So it's going to be at 225. So it's going to be an asymptote here at 225. The next asymptote after that would have been 180 degrees later. So we had 360 plus 90 and then plus 180. So the next asymptote would have been at 630. Divide that by 2 is going to be at 315. Okay, so that's all about asymptotes. So we're basically just getting this whole pattern here repeated twice. And then we can draw in these bits here. So it goes up like this, then this shape here. And then going to get a positive one here. And then a negative one down here. And then we're going to get the start of the next one here. Okay, so we can see that it's this shape here. Okay, this graph here is being repeated twice. between 0 and 180. So you've got one between 0 and 180, and then you've got another one of the same here. So we've got two waves or two periods in the same amount of time instead. Now the last transformation to do is to take that graph and shift it all up by 1. Okay, so it's going to look approximately the same as this. Maybe I'll just move these. Actually, no. Yeah, let's copy this one, and then I'm going to edit this diagram. Okay, so it's all going to be moved up by 1. So instead of going through 1, it's going to be up here at 2. Same with this bit here, it's going to be up at 2 instead of 1. This branch here is also going to be as high as 2. This one, this was at -1 down here. So if I move it up, it's going to be at 0. And the same with this part here. Okay, so that is what my graph would look like. So this is now 1 plus sec 2 theta. Okay, so always try and draw the most basic graph first. So in this case, it was sec theta, and then apply your transformation step by step. That's normally the most mistake-free way of doing it. Okay, there's some other graphs here. These are from exercise 6b, and these are all transformed ones. What I'd suggest you do is maybe pick out a few of these to have a go at sketching by hand, and then see if you're correct using Desmos. Okay, so if you go onto Desmos, you should be able to just type them in, or if you can't type in one of them, so I think cosec x wouldn't let me type in earlier, you can obviously type it as 1 divided by sine x, and you can use that to help you. Okay, and you can use that to check your answers. There's answers in the back of the book as well, but that's probably a nicer way of doing it using some graphing software. Okay, now I want to look at using these trig functions, but a bit more algebraically, and this will lead on later to some more trig proofs like we did with the year 1 content. So for part A, how can we try and simplify this? So sine theta, cot theta, sec theta. I suppose the first thing to do is write these as either just sine, cos, and tan. So the first one is still the same. The second one is 1 over tan theta. And the last one is 1 over cos theta. So I could write, well, the first thing I'm going to spot here is actually this one and this one. Sine theta times 1 over cos theta. I could write that as just sine theta over cos theta. And hopefully you recognize that that is tan theta. So I've then got tan theta times 1 over tan theta, which then gives me 1. For the second one, sine theta cos theta times sec theta plus cosec theta. So again, I think the first thing to do here is probably just to rewrite them in terms of sine and cos and tan. So sine theta, cos theta, they're fine, they can stay. Sec theta is 1 over cos theta plus cosec theta, that is 1 over sine theta. Now if I expand this out, so the first term would be sine theta cos theta times 1 over cos theta plus sine theta cos theta times 1 over sine theta. And I hope you can spot I've got a cos theta divided by cos theta here. So this is just going to equal sine theta. Plus this one, I've got a sine theta times 1 over sine theta, which just gives me, well, they cancel out or they give you 1. So this term is just going to become cos theta. And I think that's probably about as simple as we can get there. Okay, here's a couple of trig proof questions that we're going to have a look at. So let's have a look at the first one. So prove that cot theta cosec theta over sec squared theta plus cosec squared theta equals cos cubed theta. Now in these questions, like we did them before, you have to either start with the left and rearrange it by doing some simplifying like we did in the last slide to get to the result on the right, or vice versa. I would normally always start with the one that looks most complicated, and then you could simplify it down to get the thing on the right. So I'm going to start at the left-hand side here. So cot theta times cosec theta, all divided by sec squared theta plus cosec squared theta. Okay. I'm just going to use some of the definitions that I've already got for these. Now cot theta, that's obviously 1 over tan theta. And we also know that tan theta is sine over cos. So 1 over sine over cos is going to be cos over sine. Okay, that's sometimes quite a useful identity to use. Okay, so instead of tan being sine over cos, cot is cos over sine. So you've got cos theta over sine theta times 1 over sine theta on the top of the fraction. And on the bottom, I've got 1 over cos squared theta plus 1 over sine squared theta. Okay. Now let's keep going. Let's look at the bottom of this fraction a bit more. I'm going to try and add these fractions together. So I'm going to create a common denominator of sine squared cos squared. So I'm going to times these two together, which would mean I'm going to leave the top the same. Actually, no, I will simplify the top at the same time. This can just become cos theta over sine squared theta on top. And on the bottom, common denominator of sine squared cos squared. On the top of that fraction, you're then going to get sine squared plus cos squared. Okay. Now, if I keep going from there, it doesn't matter that I've got a fraction on top of a fraction. We can sort this out. The top I will leave as it is. So it's cos theta over sine squared theta. Over sine squared plus cos squared, hopefully you recognise that as 1. That was one of our identities. So we've got 1 over sine squared theta, cos squared theta. Now, when we've got a fraction divided by another fraction, it's probably best to write it as a multiplication. Well, that's certainly how I will do it instead. So in the same way that dividing by a third is the same as timesing by 3, we can say that this is the same as timesing by the reciprocal of this, which is sine squared theta, cos squared theta over 1. Okay. And now if I multiply these fractions here, I will end up with sine squared theta cos cubed theta over sine squared theta, which then gives me my desired answer of cos cubed theta. Okay, so slightly more complicated than the ones we've done before, just because you've got more functions to think about, but putting them all in terms of sine and cos is probably a pretty good approach to help you sort it out. And make sure that you're comfortable with things like this for adding fractions. Okay, it's just this exactly the same method as you would do for if you had 1/3 plus 1/5. Okay, you would write them both as 15ths. Okay, same idea. Okay, then the second part, hence why this equation equals 8 has no solutions. Well, this is obviously exactly the same as this. Okay, I'm going to do part B up here. So we can rewrite this whole thing here as just cos cubed theta. So cos cubed theta equals 8. So that would mean that cos theta, if I cube root both sides, would be 2. Well, the reason that's got no solutions is the cos graph looks like this, and it only goes between 1 and -1. Cos theta equals 2 would be a line up there somewhere. Okay, so my explanation would probably be that the graphs y equals cos theta and the graphs y equal 2 do not intersect. And drawing a little diagram like that is always going to be helpful too. In this next pair of questions, we've got equations to solve rather than proofs. And again, this works just the same way as the solving trig equations we've done before. We've just got some new functions to deal with. So for part A, sec theta equals minus 2.5, and we're solving it between 0 and 360. Now I could use the graph of sec theta. Okay, I could plot sec x and I could plot y equals minus 2.5. Okay, and I could then find where they intersect. That's what I'm actually doing. But if we can avoid drawing the sec graph, then that's probably for the best, really, isn't it? So we're going to do it in terms of cos instead. So sec is 1 over cos theta, it's minus 2.5, and then I'm going to do the reciprocal of both sides. So cos theta is going to be 1 over minus 2.5, and 1 over minus 2.5 is minus 0.4. And now we've got an equation which looks a bit more like the equations that we solved before. And we've then just got to solve it between 0 and 360. So theta, I can just do inverse cos of minus 0.4. My first answer is 113.6 degrees. And then the next answer I can do 360 minus that. So that would be 246.4 degrees. There we go. Now for question B, we've got cot 2 theta equals 0.6. So I think the first thing to do is to change it into tan rather than cot, because obviously our calculator does not have a cot button on it, but it does have a tan button on it. So we can rewrite this as tan 2 theta, or 1 over tan 2 theta, is 0.6. So that then means that tan 2 theta is 1 over 0.6, which is 5/3. And then we've got to solve this equation. Now you can either do it by substitution. I think I'm going to do it without a substitution. I'm just going to find out what 2 theta is. So if I do inverse tan of 5/3, then I will get 59. That's my first answer. To find multiple solutions for tan, I just add 180 each time. So that's then 239, 419, and 599. The reason that I found so many, because obviously these are beyond 360, but I know that at the end I've got to divide them all by 2. So I've gone and found sort of twice as many as I would normally, because I know if it's tan 2 theta, I'm going to have twice as many solutions. The graph has been squashed by 2, so there'll be twice as many intersections. And then I could just half all of these to find theta. So that's 29.5, 119.5, 209.5, and 299.5. Okay, and then those are all my answers. Okay. To practice these skills, so to practice a bit of simplifying and a bit of solving equations, I'd have a look at exercise 6c. There's quite a lot of questions in there, so I've suggested maybe do just every other subpart or something like that, however many you need to do to make sure you're happy with them. But try and make sure you do both a mixture of the proof questions and also the solving questions.